Hey, what's up, guys? Yeah, so today I want to talk about skin category skin and the fiber products of skins. Okay, so this video most of them just the terminology, and I hope you guys subscribe to my channel. Okay, so just quickly recall that the ring space morphism, right? So the ring space is basically a topological space, and the OX is a sheaf of rings. And if you have, so we say that if you have this, uh, let's say phi and let's say f and phi, are the pair, which we call the morphism of the ring space from XOX to YOY. So these are morphisms. These are morphism of ring space. Basically, you need to require that the F is continuous map as topological space. So this is continuous. And the second one is that this is a sheaf, right? So you need to have the morphism between sheaves, and this O, so F will have the direct image, right? So you have a sheaf of morphism, which from OY to direct image, sheaf of OX. Okay, so let me just recall this. Sheaf of image are basically the sheaf you pull from Y to X. Yeah, so this definition is very simple, right? You need to have a sheaf morphism on Y, so you put direct image, you push X to Y. Okay, so this definition is very simple. We take on any open set U on Y, then you just the F inverse is open, right? Because F is continuous. So the natural definition will be O X F inverse U, right? Because you take this on U, and then you take F inverse on U, so it becomes OX. Okay, so this phi is the sheaf of morphism. So this is morphism of sheaf. Okay. So if you have these two, then this is called a morphism of ring space. Okay, and quickly define. Remember, there's a definition called for a local ring space. So XOX is a local ring space if OX X on each stocks is local ring. Okay, so local ring basically means that there's a unique maximum ideal. Okay, so let's denote the M of X. Okay, so and the kappa of X or K of X, if you define the local ring quotient is maximum ideal, this is called residual field. Okay, so it's just some terminology. Okay, and okay, so we can incorporate this morphism ring space to the local to the morphism between local ring space. Okay, so the requirement for local ring space is that we added a condition here. So we say that F phi is locally the morphism between local ring space, morphism of local ring space. If this phi from the stocks f of x to push forward of x at x is local ring map. Okay, local ring map basically means that you map maximum ideal into the maximum ideal. Okay, because there's a unique maximum ideal. Okay, and the standard local ring space that we proved in a previous lecture is a fine skin. So if you start from a commutative ring with identity, you can define X to be a spec A, and the edge stocks. Let's say So this is edge stocks localized at prime ideal P will be defined to be just AP. So this is a shift. So shift. Okay, and AP is just the A delete P inverse times A. So this is the localization of ring. And the previous video that I think whether I have a video proof that AP is a local ring. You can prove that PAP is the maximum ideal. Okay, this is not difficult. Okay, so now then we have introduced the skin, right? So we have introduced the skin. So skin basically is like for each X belongs to S, there is an open neighborhood. There is an open set U, such that the U is isomorphic to or basically let's say SOS. The U and the OS restricting on U is as an isomorphism of the ring space for the affine skin. So shift A. So it should be spec A. Okay. Okay. So now let me just define the morphism between skins. Okay. So since we have defined what is skin, right? So we can define and as we know that skin is a local ring space. So we can define what is the morphism between skin. Okay. So the simple definition is just to say that we just say that morphism between skin is just the morphism between the local ring space. Okay, so definition. Let's see. Okay. So a morphism of skin, let's say somebody give you two skins, X on X and the Y on Y, is a morphism of, let's say, phi theta from X to OX, from Y to Y of local ring space. Okay, so skin is like special local ring space such that each point has a neighborhood which isomorphic to a fine skin. So a natural definition for the morphism of skin is just to using the morphism between a local ring space. Okay, so here that we can get the category, because you can check that the morphism, the composition of two morphisms is still a morphism of skin, and there is identity. It's all category of skins. Okay, and right, a simple example is that if you take the subset of local ring space, open subset, then there's a natural morphism of skin where U OXU restricted and then put in X and OX. This is usually called open immersion. Okay. And there's a theorem that I will prove in the next video, but I think it's not related to what we want to say. Okay. Now the next thing I want to define is so-called S skin. Okay. So this is very simple. If there is a morphism, so from X to, so now I'm very lazy. I omit the structure shift. If you are from X, which is skin, there's a morphism between X to S. Then we call X is a S skin. Or basically, or sometimes we say that S is a skin over S. Okay. For example, sometimes if S is fine, for example, if S is a spec A, then we will call X is a skin. Okay, so for example, if you take the projective space AN, there is a skin. Because we know that there is a cover, right? There's a cover that there's a fine cover for the projective space, right? Okay, so you know that this is a skin. Okay, so obviously that if you have this such object, then you can define a morphism between a skin, right? So if x, y are a skin, then the one can define a morphism, u from x to y. It's called the morphism of a skin if you have commutative diagram such that x map to s and the y and the u such that this is commute. Okay, so obviously this is the same if you know something like vector bundle or something like covering space. This is almost the same, right? For example, for the covering space for covering space, if you have covering space from x tilde to x, then you can say the morphism between the covering space is like x1 tilde to x2 tilde u, such that these are commute. If you're talking about vector bundle, then you can define e to b. Let's say b is a base and e is a vector bundle, right? So you can also define this. So it's exactly the same thing as these two. Okay, but in this case that we define as this. So this is a relative version. Okay, so here that you can work on category of asking. So usually this is the relative version. So it's like sometimes you're not convenient to work with skin, but you can work with the S skin, which is a skin relative to some space. Okay, so the final thing I want to define is the fiber product. Okay, this is very, very hard, very amazing. But maybe in the future that we can say more about this. Okay, so if you have two XYR skin, then I define the fiber product of X. So the notation is this: X fiber product with Y over S. Is that you can find a morphism from. So this is a skin, right? But you are not only provide skin. You also need to provide a two morphism of skin, right? So one is this, one is this. So this is basically the category objects, right? Okay. Such that, so these are functor, okay, such that for all S skin Z, for all S skin Z, and S morphism, if you have two S morphism from Z to XF and the Z to G of Y, there is a unique S morphism theta from Z map to X, Y, S, such that if P1 composite with theta, G is P2 composite with theta. Okay, so let's understand this. So basically, you're just saying that you need to provide these three. So this is you need to provide. So all three of them are called fiber product, such that for all three of them, you have uniquely this. This is called the fiber product of skins. Okay, maybe let's do some diagram. Okay. So the diagram looks like this. You have X and Y, and then there's a fiber product. Okay, so these are P1, these are P2, or such that for every Z, if you have Z to X, call it F, Z to Y, call it G, there's a unique. Okay, so there's a unique maps data. Morphism from S morphism from Z to the fiber product such that all these diagrams commute. Okay, so this is called the fiber product. This guy is fiber product. Okay, so it's very amazing, right? If you define some such like powerful object called fiber product. Okay, so the theorem, which is a very deep, very long and hard long proof that I will not give here. Then you can check for Cal or the Harshon. So the theorem says that fiber product exists for any skin S skin X and skin Y. Okay, so proof is very long. So the proof, maybe if I understand it, I can talk in the future, right? But the proof is very difficult. You need to usually for first you can assume that both X, Y, Z are fine. And if this works, then you try to decompose some of them into a fine, and then you check step by step. And hopefully, finally, you can prove that this big guy exists for the general scheme. Okay, and so one thing I want to say is that, for example, probably it's not obvious, but these fiber products looks like a Cartesian, right? If you start from a flat plane with n dimension, working on the flat plane for n dimension, do the fiber product over the real, then or any ring, then it will become m plus m. Okay, and yeah, so there's this finally talks on property. The properties of a skin. Obviously that probably not obvious, but X S. Well, if you take a skin and with S, then this is the same as X S, the same as X. Okay, this is almost the same if you do like the Arpedian group like tensor with Z, you get the same group. And also it's commutative, and there is associative. These are all non-trivial facts. Okay. And then there's the idea called base change. So base change looks like if you have the S skin, and then you have another map from 2 S prime to S, then you can do the fiber product, right? So this guy usually called SX prime, which is a base change from S to S prime. Okay. Okay. And if you have this kind of map, it's called phi prime phi, and your S prime base change into S prime will be the same as just directly base change. Okay. And also this guy has the functorial property, which I mean that if you have start from X prime, Y S prime, and do the fiber product on X prime, then you're isomorphic to X, Y, and S, and S prime. Okay. Okay, so this is the property of S skin. Proof is very difficult. I mean, for the fiber product, it's very long. So yeah. But in this video, I just want to give you the terminology of why you can talk about category skin and fiber product skins. Okay, see you guys next video.